Let us begin. All right, so here we are on page 190, and it says, so this first part is just transformation of variables. We're not even hitting logistic regression in the beginning, so this is just when you see a scatter plot like this one, I can even see this, it says, all right, this pertains to last semester's 1,209 responses to 2 survey questions. It's kind of interesting, actually. Number 1 is, when you graduate, are you more interested in doing good, helping others, or in doing well, gaining material resources? So on a scale of 0 to 10, rate where you fall. 0 is doing good, and 10 means doing well, getting rich, money, or altruism, basically. So, and then I also wondered if it related. I would think that if you're more interested in making money, then you would answer, it would correlate with your expected income. 20 years from now, 20 years down the road, how much money do you expect to make per year? So I thought that people who answered they were expecting a lot cared more about money. So I thought there'd be a positive correlation. This is not logistic regression. I'm trying to predict expected income from, and that's a quantitative variable. But when I look at this, look at the question says, look at the y values. They're all squished at the bottom of the plot. All the errors are above. There's no errors below. Because if you actually looked at this data, there's it's very right skewed. So we looked at the histogram of expected income, and you can see it looks like most of the people answered 0. Well, nobody expects to earn 0 who graduates from U of I, right? So it's just that some people said 150 million, wait, lots and lots of money out here. And so to fit everything on the scale, everybody got squished in. So you'd call this very right skewed. Because there's people the extreme values are really far away, right? So you look at this and you see, I want to transform these y's to make it look more normal. So when you have a right skewed, like this, long right-hand tail, right skewed, what you want to do is you want to bring some of we want to bring some of those values in. So we want to basically just look at logs or square roots. We'll bring those big values in more. So when you right skewed data, what you want to do are these 3 things right here, but you have to read very, very carefully. It says, which transformation would not work? So these right here work for right skewed, long right-hand tail. And these are the transformations that work. They do the opposite. These transformations work for long left tails, kind of like our exam data. All right, but the question said not work, so which of them would not work for this are these 3. So circle all. So you have to read it carefully. And part of the reason this happens is because I do 2 different versions. And so sometimes it might, just read it carefully because I want to make them of equal difficulty, so I'll just change the sign on some of the problems one way and change it the other way for the other ones. Okay, so any questions on that? So now our next one is below are histograms for the transformed income. So this is a big hint. Okay, look what happened. And so which of the 6 transformations here do these histograms depict? Below each histogram, circle the transformation. So, all right. So, look, this one made it normal the way we want it. And this one didn't go far enough. So remember that we talked about this, it's in the first chapter here, that basically this is the most mild transformation. So, and this is the next one. And this one, 1 over y would do what? Well, this data looks like it runs from very small numbers, like it's really, expected income in thousands. I don't know, it starts at 10,000 or something, but you can't see it because they're all squished together here. But to 150 million or something. So if you did 1 over these datas, it would just go between 0 and 1. You know, it would also make the biggest one smallest. Basically, we've been doing the square roots and the logs, and these are the ones you usually do, and this one, you can see this one didn't go far enough, and this one looks pretty good. Okay? So the next one is below is the scatter plot of the transformed. Okay, so now we have the log. It looks better. Boy, this is so hard for you to see. It's going to be worse for people online. Let me just see if I can. Wonder why it's hard to see. Are you having difficulty seeing it out there? You are? How about if is this any better? No. What, there's something, wonder what's going on, why it's doing this. That's not any better, is it? Maybe it's a small print. I'll just zoom in a little more. I think that will help. Is that better, a little better? When I write, it looks better. Okay. So now this is in your books too, and it says this is the transformed. It's log. So below is the scatter plot of the good or well ratings versus the log of the expected income on the left hand, and this is the residual plot on the right. So you can, they look very similar just because this one has a very slight slope, and this has a 0 slope. It's kind of, they don't look much different than each other. All right, but here is our equation in the log, and it says log of the expected income is equal to 4.3 plus 0.11 times the ratings. All right, so use this above equation to estimate the log of someone who just was right in the middle of the road, right in the middle of between helping others and making money. 5. So all we have to do is just put a 5 in for that. So that's super easy. Just solve that. So it's just 4.3 plus 0.11 times 5. And whatever we get, we put there. And that's 4.85. Okay. Whoops, it's not 4.85. I saw a dollar sign there, and I said, that can't be right. We're talking about logs. So it's 4.85. My eyes aren't very good either. This is what I wanted to do here. 4.3 plus 0.11 times 5. That's a logarithm. It has no dollar sign there. Very sorry I put it down here. Okay, so now what's the next question? Now estimate, so let's cross that out, that's wrong. Now estimate the student's expected income. Well, if this is the log of the income, that's the log of the income equals that, we just want to anti-log it. So it will just be e to the 4.85. We anti-log that, and then we get 127.4. 0.74 is what I got. And that's in thousands of dollars because that's how it was originally, in thousands of dollars. All right, so all I did was anti-log. And now what am I supposed to do? Any questions so far? All right. Yes. What would be the 1 over y? We never use 1 over, we hardly ever use this one or this one. 1 over y, if you recall, will get rid of this right-hand tail, but it also makes the biggest values the smallest ones. So here you have 150 million, you have 1 over, so it would be between 0 and 1, the way the data is, so it wouldn't be, because everything's over 1 here, so everything's bigger than 1. Even though it looks like it's 0, nobody said 0. It's hard to see it because they're all squashed in there. You understand? Good question.
Can you explain one more time for the b part? Like, why do we use the square root of y of y?
Why is this the square root of y?
Yes.
You could just look at these numbers and take the square roots, and you'll see that they're similar to that if you want to do that. That would be another way to do it.
And you turn a continuous graph into a histogram?
No. I made this continuous. They're both histograms. Yeah. Hey, quick thing, and this is a good way to study. Let's just do this. It will make it more interesting, too. So if we go over to the let's just look at the data. Okay, so this was expected income. So we can do that. We can just go to our data program. This is where I got this from. And just look at Stat 100 data from last year. That's what that was. It said, all right, so let's find it. It was survey 2, Stat 100 and 200, survey 2 from fall, Stat 100, survey 1, Stat 100, survey 2 from spring. Whoa, sorry. Here, I want the Stat 100 sets. All right, so lots of data sets here. Help me out here. Do you see it? Stat 100 and Stat 200, survey 2, that's it. So, all right. So one of the questions I asked was, when you graduate, are you more interested in doing good or doing well? And then what's your expected income? So when we look at the scatter plot here, what happened is, so you look at the x variable, I was predicting your attitude, whether you were doing good or well, scale, right? And I was predicting from that how much money you expected to earn. So that should be right here. And it looks like, here you can see it's happening better if I put some jitter around it, because I'll put jitter. Where's my jitter? Okay, this is what's happening. Lots of people answered down here. Well, they didn't answer 0. It's just some people answered such high numbers here. So if I put the regression in here, and then you can look at the errors, they're going to look very similar. But if I put the, and what is R? R is 0.1, and you can't really see stuff very well. So what I'm going to do instead, because is look at the histogram. All the errors are giant up here, and basically the program sees these as just 1 point, all these, even though I blew them up. It really sees it like, more like that. All right, so now I'm going to go to histograms. So I go home, and I'll go to histograms. And now what I want to do is, let me show you what this looks like. When I ask you what your expected income is, it looks like something's wrong, like there's a mistake, right? We can't see anything. That's not a continuous data. That's like a crazy, it's just, we're all bunched up here. It's like you have no discrimination, because some people just answered these huge, huge numbers. This is in thousands. So this is not 150,000. This is 150,000 thousand. This is 150 million. So what we're going to do now is we're going to do a transformation. So we do a square root, and what's this going to do? It's going to bring these numbers down more, and so it will be able to spread this out. Right now, the scale is too big to include these numbers. You can't see the numbers that people actually answered. So that's why we have to take a log to even see them. So we're going to take a log. Well, first we'll take the square root. It will do somewhat of a job, but it didn't go far enough. And now we take the log. Does that help? Does that help answer your question? And then how many intervals you do with these logarithms is just like, I just wanted to display it nicely, and that I can choose how I want to bend things. So I bend them kind of like that. Does that make sense? Does that help? All right. So, I mean, you have to log things in all the time just to be able to see it. If you care about the answers, you just can't see it until you go on a log scale for many, many things. Yeah, you should. That's right. Here, yeah, we do. You should know that, because we talked about it, and just watch the first lecture in this section, and I'll show you what we talked about. We went over it, and I explained why and stuff, and it was right here. So you can understand page 158, and I explained it better in class. So you can just go back to the lectures. That's a good thing to do. If you're not sure of something, just go back to the lectures, and I drew pictures and so forth. Okay? Does that help? Always do that. If you don't understand something quite, just go back and just zoom through that part of the lecture. And, I drew other pictures too. Okay. So,
Any other questions? Yeah.
The log y always gonna look better than the square root of 1.
The log is always more extreme. Think of the log as an exponent. Like if you took the square root of, he says, is the log always more extreme? And well, yeah, if you have like let's say we have a scale like this and you have 0, 10, let's just do log base 10, right? Then 100 is going to be 10 times further out there, so that'll be 10 squared. These are the logs, right? And then you can have, I can't even fit 10 cubed on here, right? But if I take the logarithm base 10, if I took the log transfer, if I took the square root, then 100 would go to 25, whereas if I take the log, it goes all the way to 2. It brings it in further. A log is an exponent. So if I do a log transform of this, here's 10, I can put 25 is going to be about there, and I'm just on a regular scale, and then I take a log base 10, because it's just easier for people to see. Log base 10 of that data, well then you're just going to get what? You're going to get 0, right? The log of it's just, you're not going to have a 0 there, but like 10 squared is going to come all the way down to 2, right? Because it's just the exponent. But if I took the square root of that, then I'd get what? The square root of, you get 0 here, and the square root of 25 would be 5. The square root of 100 would be 25. You see, it wouldn't take it down as far as taking 10 squared all the way down to 2, and 10 to the first all the way down to 1. See? And 10 to the 0, which is 1, would be 0. And if I had 1,000, it would take it way down. See? It does a more extreme. And then you spread this out, and you can see all the numbers better. Does that help? All right. Can we move on? Yes. When I do what? When it's left skewed, like let's just go back to the notes. When it's left skewed, like this, when you square it, what you're going to do is you're going to spread these numbers out. They're all bunched up here. Think of our exam scores, okay? Think of our exam scores. Sometimes, like in Stat 100, they'll be like, most of the class will be between 90 and 100 or something. And then there's a bunch of people out here, and there's really not much discrimination. So some people try to normalize that. One way to make it more is you could spread those out by squaring them. Or if you want to go more extreme, you could cube them. If you want to go even more extreme, you can put your exam scores as an exponent, e raised to that exam, and that would just really skew these out. Okay? So 1 point difference becomes much bigger out there. Okay? So that's, so the idea was this, that what you want to do is first try, this is the mildest, this is more, and this is the most. You first try the square root, then you try the log. All right, so now let's move on. It's been a while since we did this. I don't blame you. It's hard to remember. All right, now, compute a 95% confidence interval for your estimate in part 2. Okay, so this one, you can't just say 127.74 plus or minus something. You have to go back to, you have to put error, we want to put error bars around our estimate, but the standard deviation of the errors here is for the log. So we have to put error bars around the log, not around this one, right? So we have to say, we have e to the 4.85, so we want to say we'll say e to the 4.85, which is 127.74, but we're going to say minus 2.85. 2.6 and e to the 4.85 plus 2.6. So basically, or you could do it in 2 steps, right? You could say the first step that you do is you put this 95% confidence interval. This is the way we did it in the homework. I had you do it in 2 steps. I said a 95% confidence interval first for the log of income. For the log of the income, right? I did that, and that's equal to this part right here, this to that. And then you just exponentiate it. And then you just say a 95% confidence interval for the income is just doing e to that. Does that make sense? This part right here is just that. And I'll just color code it to make it a little better, easier to read. All right, so for the log, it looks like for the log, 95 is this part. And then for the confidence interval itself, you would exponentiate that. You raise it to that, and you get, I got 9.49. 9.49. And here I got 17.986. And this is in thousands. So now you have dollars there. Okay. Anything else? Let's see. Should we move on? So now 95% confidence interval for the expected interval income of another student is this. So what's his expected income? Remember, it's not symmetrical around income. That would be the geometric. The income would be the geometric mean. So you take the square root of those two multiplied together, of the product of those two, of 5.47 times 992.27. And that will give you right in between. Any questions on that? All right. If you forget that, you could just look backwards what you did. I gave you the endpoints like here, so you could just raise e. You could just, you could take the log of those two. The log of those two, and that would get you back to these two things, and then you could average them. And then you'd have to exponentiate it, so it's probably easier to do this. What I mean is if you wanted, you could, you're given those two things, you could say, okay, I'm just going to get I could take the log of those. So you take the log of, I don't know if this would help you or not, it probably wouldn't, 5.47, and then you could take the log of the other one too. Those would be the endpoints of the log of 992.27. Then halfway, that will be symmetrical. So halfway, you get that answer, and then exponentiate that. So you'd say e raised to that whole thing. And that would give you the same answer as that. All right. But let's move on. Okay. Now here's an easy one. Well, actually, this wasn't so easy for people. It should have been, but I don't know why but it wasn't. So each plot will be the answer to exactly one of these questions. All right? So which plot or plots are well suited to linear regression analysis as they are? So which one is just, looks like it's fine. This one has a curve. This one has a fan shape. This has two groups. This one's two. This is the only one that looks pretty good, as is. So that's plot E. Now that's not going to be the answer to any other question, because I said that each one of these, these 6 will be the answer to these 4 questions. So some of them, that's what, are going to have multiple answers. So that one's eliminated. Now, which plots show a curvilinear trend? So which ones? Well, this has a curve, and this has a curve. So those 2, I don't see any others that do. So there's B and F. Okay? So now you know those aren't going to be answers to any others. So we only have 3 left and 2 questions left. So let's look at the rest of them. Which plots should be broken into subgroups since they show 2 distinct groups? Well, that's an easy one. This one has 2 distinct groups, and this one does. All right, so that's A and C. And then that's the only one that's left is that. But which plots are linear, like they're linear, but would not be suited to using the standard deviation of the errors for building confidence intervals? It's not suited because it has this fan shape, and the errors aren't the same across all levels of x. So that is D. And that's pretty easy. All right. So now let's look at the next one. And it says, for which of the following would it be appropriate to use either simple or multiple logistic regression? Well, using multiple regression, when do you use it? Simple or multiple regression? Okay, what does that mean? It's suitable when what? So you have to remember, you use logistic regression when what you're predicting, the y variable, is binary. Yes, can be coded as 0, 1. Yes or no. All right? So for these, predicting whether you get an A, B, or C on a test from hours of studying, well, there's 3 categories here. Predicting an A, does somebody get an A, B, or a C? So there's 3 categories. So you can't use logistic regression. Either an A, if you want to predict whether somebody's going to get an A, or whether they're going to get a B, or whether they're going to get a C, that's 3 categories, and logistic regression is just for yes or no. All right? Predicting whether or not you get an A on a test, whether you get an A on a test, get an A or not get an A, that would be yes. Does that make sense? I'll give you a minute just to do the rest of them, because this now you know for sure the idea, and just make sure you can get those right. If you've finished that, I would move on to the next one, the next problem, because that you know how to do. Make sure you know how to do those, remember? Okay, so predicting surviving breast cancer 5 years. It's a yes or no question. Does survive or not survive? So that's yes. Predicting how many years, that's a quantity, years of survival. That's how many years. You can't phrase it as a yes-no question, so that's no. Predicting the log of the income from years of education, that's a quantitative variable. You're predicting log of income from years of education, so that's no. Does that make sense to everybody? Does that make sense to everybody? Yes. Say again? Yeah, whether it's a yes or no question. Predicting log is not an A. Predicting surviving breast cancer 5 years. Yes or no? Does the person survive breast cancer after 5 years? You can't say yes or no, how many years does somebody survive? That's, the answer is a number, not just yes or no. All right, so now these, I think, do you want me to go over I mean, these, just remember that P, okay, so you're given one of these and you want to fill out the rest of it. And remember that P is equal to what? In terms of odds, this is odds over 1 plus odds. Then you have P and 1 minus P. And your odds are P over 1 minus P. So for example, do you want me to just do one? Do you want me to do these, or do you? I mean, like if, for example, 0.25. All right, that's the odds. So your P would be 0.25 over 0.25 over 1 plus 0.25. And that's the same thing as 0.2. That simplifies to 0.2. So then 1 minus P has to be 0.8, correct? Then you need your calculator to do this one, to do this. But here we can look over, we can look at one that's a fraction. Like here, do you want me to do these or not? Raise your hand if you want me to do any of these. Okay, so let's just do the next one then. It says express P, 1 minus P, and odds as fractions for columns 2 and 4. Columns 2 and 4. All right, why don't we do this column first, and then we'll do 2 and 4. All right, so here, 0.2 is 1 minus P. So they have P and 1 minus P have to add up to 1. So this is 0.8. And then odds is just P over 1 minus P. So that's just going to be 4. All right. Now we can do this one. If 1 minus P is 5/9, then P is going to be 4/9. And the odds would just be 4/9 over 5/9 or 4 over 5. I made these symmetrical. I won't always make them symmetrical, but here I made it symmetrical. Now your odds are 5 over 4. So you can, another way that we've been thinking about it is that means, okay, so the total number of outcomes, this is success over failure. So the total number of outcomes is 9. So this is 5/9 and this is 4/9. And now we should take out our calculator to do the rest of it. So the log of 4 is 1.39, rounded to 2 decimal places. So you really wouldn't have to do 1/4. You know it's going to be negative 1.39, but you can just do it just in case, just to check. And so you'd say log of 1/4, and it is. Sorry, that might not have been on there before. Okay, so now the log here, we want to take the log of the odds, so we have the log of 4/5. So we can do that. So we'll take the log of 4/5, 4 divided by 5. And we get negative 0.223. All right. Rounded to 2 decimal places. So this one would 5/4 would have to be 2.22. All right, and now the log odds. So then you exponentiate it. E to the 0 is 1. And then this is odds are just 1 to 1. So that's a 50-50 chance. These we've been through a lot, that saying your log odds are 0 is the same thing as saying your odds are 1 to 1 or 50-50, and saying the probability is 0.5. Those are all the same. Okay? And there's lots of practice on this, and you'll be sure to see a problem like this on the exam. So this is just, everybody gets this right, because all you have to do is go to just practice it. It's just easy. And there's tons of practice. Whereas homework problems like this, so you can go back to the practice homework and just do it over and over and over again with different numbers, and everybody should get all these right. In fact, everybody always does get all these, right? Okay, unless people just didn't try it all. Now, let's look at this. And a lot of, this exam is really not too hard that way. I mean, it's very manageable, and you can do a lot of practice. A lot of it, for people who have difficulties, they're just not used to thinking in terms of logarithms, and all that comes with practice. That's all it is. So if you just do the problems over and over again, you'll get a good feel for it. All right, so now let's look at the next one. Okay, in our last survey, students anonymously answered 3 questions. Would you date someone who's transgender? How many children would you ideally like to have, and are you a male or female? So suppose these students were randomly selected from all U of I, and above is the output of the logistic regression model used for predicting the probability of dating a transgender from whether you're male or female and from the ideal number of children you would want to have. So we want to know, here's the model for that. So, so let's look at it first. Let's just interpret this. Here's our intercept. This is the intercept and our slopes. So let's just look at what the equation says. And it says the predicted log odds for whether you'd say yes or no to dating a transgender. I asked you guys that question too on your survey. I haven't done a model from it yet though. All right, so we'll fill this in. So it says negative 1.604 plus for gender 1.002, and for the number of children, it's negative 0.3823. So just looking at this, if it's positive here, if you have a positive number, we only have one positive number, that's going to increase the log odds, which would increase the probability, right? And gender's the only positive one, so that is coded 0 for males, and for females, it's 1. So just looking at this, you can tell, okay, females are more likely to date a transgender, to say they would date a transgender. And this, you can see, this is negative. Whether it's positive or negative here is all I'm looking at. So here you see this one's negative. That means the more children you want to have, what do you think? The less likely you would be to date a transgender, because your log odds are going down, which means your odds go down, your probability goes down. All right, and that makes sense, because if you really wanted to have children, maybe you think a transgender wouldn't be able, lots of times transgender people might not, if they, would not be as likely maybe to be able to have children. Maybe that's why. And then that's how that you would interpret this. So what does it say? Are males more or less likely than females to date a transgender given the same number of children they want? So everything, let's say male and female want the same number of children. You're just looking at this. Who's more likely? Whoever's coded as 1. Because if you put a 1 in there, then they're going to be more likely. And who's coded as 1? Females. So males, what did it say? Are males more or less likely? Males are less likely. Right? Males are less likely. Because the gender slope is greater than 0, and females are coded as 1, not males. And males are coded as 0. All right, so the more children desired, what? It's negative, so the lower the probability of dating a transgender, everything else being equal. And that makes sense. So what's the estimated odds ratio? Well, you remember the odds ratio is just e to the slope. So what is it for children? For children, and what is it for gender? This one's for gender, so e to the slope for gender is what you want here, and e to the slope for children is what you want here, and that will be your odds ratio, which is the increase in odds for each extra child. It will be since that's negative, it's going to lower the odds. And this is just, what are these numbers? Let's do it. So this means this is 2.72. That means that the odds of dating a transgender comparing females to males is 2.72 higher for females. And this is 0.68. So your odds are lower, that's less than 1, for each extra child by a factor of 0.68, a multiplicative factor. All right, so let's use the regression equation so you can know. This is just plug and chug, just making sure you understand how it works, and it helps to understand it. So for a male, and males are 0, who wants 0 children. So a guy who wants 0 children, what would be his log odds? So you just put, so his log odds are going to be negative 1.604 plus 0 plus 0. And so then what will his odds be? Odds are just e to the log odds. So it would be e to the negative 1.604. And I got 0.201. And then probability is odds over 1 plus odds. Now let's just see what I asked you to do here. Show work. Whoops, I should have put some work in there. Here's some work here, though. And round all answers to 3 decimal places. All right? You may use your rounded answers in your calculation. Okay, so I can use this rounded answer now and say 0.201 divided by 1.201 to get my next answer, which is 0.167. All right, so I'll just do the next one. The next one is what? For females, it's negative 1.604 plus, I'm putting a 1 in for females, plus 0, right? So that I got negative 0.602. Then I raised that to the negative 0.602. And I got 0.548. And then, you know, I don't have to keep doing this, do I? I think you know how to do this. This, everybody pretty much gets right, too. If you just practice that. So there's a lot of things that you're just going to be able to do pretty easily on this exam. All right, now, let's look at this one now. Is that okay if I just go on now to the next problems? Because these are, all right. So you should, I mean, really, I think people do the best on this third exam, generally speaking. And if you don't do well, it's because you didn't study for most people. All right. So now Kate wants 3 more children than Sarah. Compare their odds of dating a transgender. All right. Remember, we're doing these odds, the odds, when we're comparing odds, we're using the odds ratio. And the odds, so we're using, what are we doing? 3 more children. Okay, so we're using this odds ratio right here, 0.68 e to the slope. All right, so it's a multiplicative factor that's going to, for each additional child, it's going to be, you're going to multiply. So it's right here is your answer. It's not adding 0.68 plus 0.68 plus 0.68. You're multiplying because it's in the exponent here. 0.68 cubed. All right. Now, Kate wants 3 more children than Sarah. Compare their probability of dating a transgender. All right. Well, we really can't compare their probability. Remember that curve, the S-shaped curve. We can't, it's going to be where on that. We'd have to know how many more children, like exactly how many children Kate wanted and how many Sarah wanted, because it's going to change. So you don't have enough information. You see, you can figure out this, you know this odds ratio, which that doesn't tell you the odds, it just tells you the ratio of the 2 odds. The multiplicative increase, right? So you don't know the odds and you don't know the probability. You just don't have enough information. You just know the odds ratio. All right. The odds of a female dating a transgender are the same as the odds of a male dating a transgender when the female wants how many more children than the man? All right. So when are they going to be the same? Well, the log odds, we're just going to use this equation, and we just want to see, okay, when for females, put a 1 in there, males 0, and then set them equal to each other. So you could just say, okay, when they're the same, the odds are going to be the same when the log odds are the same. So let's just use this equation. So you have negative 1.604. I'll do the female first, plus 1.002 times 1 for the female, minus 0.3823, times the number of children the female wants, children for the female. And I'm going to set that equal to the same thing for males, but for the males, that's just a 0 there, right? And so that's not going to factor in. Times the children for the males. Okay, so I want those two to be equal. So I can subtract that from both sides. So now we're just going to solve for children. We're just going to put the children, female and male, on the same side. So we have 1.002 equals negative 0.3823, well, positive, I'm going to bring it to the other side, minus 0.3823. Okay? And what did I forget? Times that right there. So I just added that to both sides. So that's what I have. And now I'm just going to do what? Just divide both sides by 0.382. And that gives me the difference there. The difference between how many more children the female would want compared to the man for it to be the same. So whatever that is. And that's 2.62 is children the female wants minus children the male wants. So when the female wants 2.62 more children, their odds are the same. For some reason, men don't want to date a transgender as much. You know what's something really, probably shouldn't tell you this, but it's reminded me. I went to, oh shoot. Well, I can tell you this because the sound went off, so it won't be on anywhere. I went to a club in Boston where I was this Thanksgiving vacation, and people started saying to me, "Are you male or female?" And it's weird. And so, and then they got this buzz around. People were thinking I was trans, and I actually experienced some discrimination for being. I'm not, but for that. So it made me feel very sympathetic to people who are. I mean, people weren't very nice when they thought that was who I was. It's a very strange feeling to first be mistaken, and they said, "Are you male or female?" And I just sort of didn't say anything because I was kind of taken aback. And I didn't say anything for another reason. I just sort of wanted to see what would happen. So I guess they assumed when I didn't say anything that I was. And then people started being somewhat aggressive to me. So it really makes me sympathetic for that group. It's a very strange feeling to do that. And then I didn't want to deny it because I felt like these people are not being very nice and they shouldn't be that way. And I don't want them to be nice to me just because I'm one or the other. You know, I didn't like the feeling of the whole thing. So this is interesting. So I guess there's just, I mean, of course you might not want to date somebody, but I wasn't asking to date anybody. You know, I was just there. So it's very strange. Anyways, neither here nor there. Okay, now, actually the mic's still on. Oh well. Now, it looked like it was off. We're almost finished here. And let's look at the next one. And it says, a fourth question asked on the same survey is, are you a U.S. citizen? Let's add citizen as a predictor variable, okay? And so now we have that too. And now, okay, so a chi-square test. So now we have 4 parameters right here instead of 3. Okay, so that's 4 parameters, 3 slopes and an intercept. And the chi-square, oh, I didn't give you the degrees of freedom here. A chi-square test was done for the overall regression effect. If the sample size was smaller, would it have been appropriate to do an F-test instead? You might think yes, because that's how it works when we're doing when the y variable is a quantitative variable. But here it's not. It's this binary variable. It's just a count, yes or no. We're counting up yes or no's. So the answer is no. And maybe you should make a note of this, and that we never, because this is one everybody got wrong almost. Not everybody, but the majority of the people. Never use an F or t-test for logistic regression. And it's explained, I explain it on page 185. So you can look at page 185 and read that for the explanation. It's because, we're basically just doing counts. And it's similar to a binomial where the percent yes or no which is like a mean, is tied to the standard deviation. So you don't have to use this F or T. Okay? So that if the sample size were smaller, would it be appropriate to do a t-test for the slopes instead of a z-test? And the answer again is no. All right, now, how many degrees of freedom would there be for this test? Well, there's 4 parameters, and it's the number of parameters minus 1. So that's going to be 3. And we can put 3 in there. And calculate the z-test. Remember what a z-test is. This z-statistic we're going to do for the individual slopes. We're going to do a z, and it's always the observed slope minus the expected slope under the null, which is 0, so we can just forget about that, over the standard error for the slope. And you're given the observed slope, like our estimated slope or observed slope in our sample. So if we want to do that for, what are we doing it for? Which one are we doing it for? Calculate the z-test for the slope of citizen. Okay, so here's citizen. Oh, it's the one that's blank, duh. So it's just 0.7664, right? Observed slope minus 0, we don't need that, over 0.2414. Okay, and whatever we get there. And, if you forget, you can just see how these were done, how these z's were done. So everybody should get that too. And that's 3.17. All right, now, is the p-value less than 5%? On this test, I didn't even give you any tables. And I might want to save paper and not give you tables. So this is big enough, you should all know with that big a z-score, it's going to be under 5%. Because you should all know that here's a two-sided, and that that the critical value is well, you should just know that's it's plus or minus 2 standard errors is going to be on the normal curve is 95% in the middle. So something like 3 is very small p-value. All right, now to test whether the individual slopes are significant, the program does 2-sided z-tests. That's what it does. Most programs do. And so that's what it's doing right here, 2-sided. How would the p-values change if it was 1-sided? Well, 1-sided means what does 1-sided mean? It just means either this side or that side. So just half of it. 2-sided, you'd have two, so they'd be halved. Compute a 95% confidence interval. This is 1-sided. It's half of the 2-sided. Compute a 95 for the gender slope. You may use 2. That's because I didn't give you the table here. For the critical value, show work. So that would be a giveaway for if you got something 3. All right, so remember what a 95% confidence interval is? it's always going to be what? For the slope, it's going to be your sample slope, what you got in your sample, plus or minus what? I told you the critical value is 2, so 2 times your standard error. So we're just using it, it's for gender, so we're using this right here. Plus or minus, that's our point estimate for what it would be in the population. And then we're going to just say plus or minus 2 of those standard errors. That's all we're doing. So this is going to be equal to 0.9997 plus or minus 2 times 0. Whatever is there. Okay? So you just add and subtract that, and I got 0.62 to 1.38. Now, compute a 95% confidence interval for the odds ratio. All right, so for the odds ratio, for the odds, this is for the log odds here, for the gender slope in the log odds equation. So it's just going to be, you're just going to exponentiate those. So I got 1.86 to 3.97. All right. And now, in general, if the two-sided p-value for the slope of x and the log odds is less than 5, then a 95% confidence interval for the slope is what? All right, here, what we're trying to do is say, okay, so you have this 95% confidence interval in the normal curve, and it looks like this. 95% is in the middle. That means 2.5% here and 2.5% here. So that's why for a two-sided, where are we? The two-sided p-value, if it's less than 5%, it means these two tails together are less than 5%. So we're outside those limits, right? Right there. And so a 95% confidence interval for the slope of x, here's 0 in the middle. So that means we're outside. We're either on this side outside or that. So if we went over 2 in this direction and 2 in that direction, 2 in this, we're not going to include 0. All right? And not including 0, a 95% confidence interval for the odds ratio then is, remember, the odds ratio is equal to e to the slope. So if the slope doesn't include 0, e to the 0 is not going to include 1. Those two statements are equivalent. The odds ratio is e to the slope, so if the slope doesn't, if your confidence interval doesn't include 0, then your odds ratio won't include 1. And it's the same thing that we were talking about before about, you know, if the log odds is 0, that means the odds is 1 to 1. There's no significant, you know, etc. All right, we're almost done here. And the last thing we need to do is this. And I think this is pretty straightforward. Let's say we're predicting acceptance to medical school and MCAT scores. All the graphs below depict MCAT on the x-axis, and the y-axis is either probability, odds, or log odds. Remember, it comes in 3 forms. And this straight line is the log odds, right? Always. That's why this is always the log odds. And the odds is this exponential curve, and the probability goes between 0 and 1. So this is our probability. This goes between 0 and positive infinity, and this goes from negative infinity to positive infinity. Okay, so we've got those 3. Now, which one depicts the log odds? Well, it's the straight line. That's the linear equation. Which one predicts the odds? That's A, and that's C. All right, you should definitely know those different, that for sure. And now the equation for which one's of which form. Well, this one is our probability form. Remember, it goes right here, it's an S-shaped curve going between 0 and 1. So this one is plot C. And this is an exponential curve, so that's plot A. All right. Judging from the plots, what MCAT score gives a 50-50 chance of getting into med school? Well, a 50-50 chance right here, you can just see the 50-50 chance is right here, so it looks like it's 5-10. Right? If you couldn't see it there, you'd also say, hey, that's the same as getting a 0 here. That's 5-10. You can really see it there. And that's also the same as what? All I'm doing is that where is it? Like on our first page. This. Log odds being 0 is the same as odds being 1, and the same as probability being 0.5. So that same score, 50-50 chance of 5-10, here, if you didn't see it, you could say, oh, right there it's obvious, and right here, oops, I went to the wrong one. Right here, what should I do? It's 0.5 here, 0 here, and it should be 1 here. So it's 5-10. All right, the score that gives a 50 chance of getting accepted has a Y value of 1 in plot A and 0 in plot B. So that's it.